Yeah, so Leo from Berkeley. I'm going to be talking about thinking DSLs for massive visualization. You'll see what that means in a little bit. And I want to point out that a lot of the demos I'll be showing here are actually with some other colleagues in my lab, Amina Torlock, Matthew Torok, Edward Liu, and then Ross Bodek, who's kind of the professor orchestrating some of this stuff. And actually, I believe in a lot of this stuff so strongly that I'm actually, now that I'm leaving Berkeley, I'm actually starting a company that will sort of incorporate some of these ideas. OK, so I think before talking about what I mean by thinking DSLs, I'd want to get a gauge for what you guys think is important. So I picked out some things I found interesting. I want to see kind of who agrees. So who thinks virtual machines have been, in the past 10 years, have been a really cool step forward and kind of excited about it? OK, cool. So that's like everybody. How about type-level computation, like dependent types? Who thinks that's awesome? All right, cool. We got clapping, some strong enthusiasm, but like half the hands. OK. How about social computing, like Stack Overflow? Who thinks that's awesome? All right, so now it's like the other half of the hands. OK. All right, how about program synthesis? All right, we got some hands. All right, how about who knows what program synthesis is? OK, so that's what I want to change. I want you guys to be as excited about program synthesis as I am. And in particular, for the second half of the talk, I'm going to be talking about doing program synthesis for parallel computing. But let's walk before we run. So I want to get you on the same page for getting excited about what's coming here. So today, it looks like most of us are programming without synthesis. So let's take a look at a common example of doing regular expressions to do some text munging. So what I'm showing right here is sed. Probably a lot of you have seen it. Like the first half of it is let's match some text in a text file. I'm not actually going to tell you what that is, but it's just some strange symbols. And then once we have the match, we're going to take the match and replace the matches. So we're going to kind of template the results and kind of pretty print it. So that's what you'd write today. You'd have to remember what all these symbols are, and then hopefully you're not programming with somebody else who wrote symbols you don't know. So let's look at a different way of writing that program. So I'm just going to go to the command line. I just did a ls. Let's pick out and let's write some stuff about a file. And we're going to use synthesis to actually do it by demonstration. So here, I took a look at some files. And let's write the regular expression for stuff that whether something's a directory or not. So I'm just going to take a look at that first character. I want the regular expression to pull out the first thing. And I'll hit the synthesize button, and here it is. So what that means is we want the match, which that's parentheses. We want to pull out a particular part, and then we're going to match whatever that first character is. So dot means anything. Now let's be a little tricky. Let's try to find out if something's executable or not. OK, let's take our examples of our files and hit the synthesize button, and here we go. I don't know how many people remember what this S means, but that's actually white space. So what that means is, OK, if we have some white space, match the thing right before it. So that dot again. OK, so I just wrote two regular expressions pretty easily. So let's write a bigger one. Let's try to get the file size, because let's try to be a little more useful here. OK, and then 102. Then I'm going to hit the synthesize button. Like, synthesis is magical, right? So I should just get the result like that, as you just saw. Uh-oh, OK, right, maybe not. So synthesis is great, but we have to do some work. So we timed out. But things we can provide, maybe we can't get the file size, but we can get close. Let's try to get the thing right before it. So let's try to pull out what that thing is. We let it run, and then bingo. OK, so as long as you have something, two white spaces, then the thing and it matches. Now, the thing what we're going to do is we're going to use this as a hint to the program synthesizer. And so one of the big kind of cool concepts about program synthesis is, first of all, we're outputting the program as the result, but also we can have the program as part of the input. So I'm going to give it a hint. Let's take in a regular expression that looked like the staff thing, provide that as a hint that we want something that looks kind of like this, but go a little further. So let's try that again. So 0, 612, 102, hit synthesize. It spins away, and hopefully it works. Awesome. OK. And so what we saw is that thing I just wrote down below is this thing here, and it was able to finish the rest of the program using that hint. Now I'm going to show you something kind of cool. Let's remove this hint. Let's run it again. It's going to spin away. And it still worked. We got the same result. So no big change, but basically same answer here. And that human intuition I had of maybe if I can give a program to get it closer, then it could finish the result for me. You can actually bake that into the algorithm. And so you can actually give the hints in different ways. I can give the hint as a program, or I can give the hint as just another example that kind of gets you part of the way there. And just to finish off this example, let's make it do something useful. Let's have it print out the file size. So for the first one, it should print out file size 0. Last one, file size 612. And 102. And then for the result, we'll give it some more hints. We want to print out the size, and then I don't really remember how the replacement syntax works, so I'll just put a question mark, and I'll try to replace the question mark with something useful. It runs. It's kind of running slowly because of this bit right here. And did it finish? Yeah, and so here's the template. So great, we just synthesized a regular expression for something actually realistic in I don't know, 1 minute. So that's pretty cool. OK, so let's go on. OK, so what did I do underneath? It actually did something really, really stupid, and being stupid was enough to be dangerous. So this is kind of cool. So the way I implemented it is I basically just enumerated a bunch of regular expressions, and then as soon as one of them passed our examples, that was it, and I finished. That took 1 evening of coding. I spent another evening make it a little faster, and now in the synthesis community, we just have a big bag of tricks for doing this type of thing. So for example, if your text doesn't have any numbers, I don't need to synthesize any regular expressions that have the /d, the character lookup for it. So I'll just remove that from the enumerator with just a prepass. So that speeds up stuff exponentially. Likewise, you saw I talked about hints of OK, if I have another example, maybe I can incorporate that to making future progress. And actually, I wrote another version of this to a lot of these tricks I just showed you in the previous page, you can actually do automatically. You don't actually have to code up. And the way I did it was I used this new system we're working on called Rosette, which probably not familiar with Rosette, but you might have heard of Racket, which is the kind of the next version of PLT scheme. And it also, on the side, it's also going to use something called Z3, which is it's a SMT solver, which is kind of the next generation of the SAT solver. And Rosette will kind of automatically let you work with both of these. So I'm going to show you how that looks like. So first, the part of the code, I had a regular expression generator. This is just kind of think of it as a recursive function that'll just, based on the depth of an AST, will just generate bigger and bigger ASTs. So here's kind of that recursion. And the idea is that for each level of the tree, we'll kind of non-deterministically pick a different thing. So for example, for the leaves of the tree, we'll pick random things, maybe a character, a number, white space, stuff like that. The trick is, though, that instead of actually enumerating these, we're generating a symbolic value. So instead of actually brute force enumeration, if we have a choose of x, we actually get a symbolic value, and if you ever apply a function to it, you just get another symbolic value. And then inside of the interpreter, it's just building up constraints. It's not actually enumerating all the things. And then what happens is once we have this kind of symbolic regular expression, we want to put some additional constraints of matching it to the examples. So on the top here, I will make a symbolic regular expression, and then I'm going to ask Rosette to solve the regular expression subject to some constraints. In this case, let's say I'm trying to pull out the first t from the name Turing. I want to assert that the result of the match is going to be t, and then I'm going to run my symbolic regular expression on the name Turing. And I run it through Rosette. And underneath, it'll turn it into SAT formulas and various other kind of optimizations, and I'll get that same result as actually you saw on the web version. So that's program synthesis and kind of one high-level notion of it. And I want to kind of step back and say, well, is mission accomplished? We generated a regular expression. Is this where we want to stop? Let's say I put this into my code. Are we happy? Now we could write it, but I think we're forgetting a very important thing is basically you need to be worried about this guy, which there's this excellent quote by John Woods where he says, always code as if the person who ends up maintaining your code is a violent psychopath who knows where you live. And you don't want to show that guy this. It's hard to write, it's harder to read. So the idea with synthesis is, one of the cool things is, it's not just a tool, it's part of you want to put it into the code layers. So I can imagine wrapping up the functionality I just showed you into a synthesized sed function, and maybe we show the output of what we expect to get, but the key part is we also, as part of the code, we show the examples that led us to thinking that's the correct code. We'll show those input-output pairs, maybe the template hint, and now when we give it to another programmer, they will read the examples, and it's a lot cleaner. You might be worried about performance, where you don't want to outrun time every time you run a regular expression to run this. But we have compilers, so just do the synthesis at compile time, and this is now part of your code. And so this is whenever you have a DSL, you should be asking, well, should I put synthesis primitives into this DSL to make it actually, not look like crazy symbols? OK, and so I showed you one example of a synthesis language. I've actually been doing a lot of, I guess what's called data science programming now, or data wrangling, a bunch of different terms. Used to be called, I guess, ETL, like extract, transform, load. And I want to show you how synthesis changes the various programming steps here. So what I just showed you was, let's say we have a bunch of different files. Now we know how to do the extract step, where it's basically just a bunch of regular expressions to get useful data, like out of your log file or your CSV. But once we have these data sources, now we have to combine it into SQL. We have to combine it into an understandable format. So we'll use something like SQL. And then once we have the data kind of centralized in a nice format, then we want to actually do the data analysis. So maybe we'll do machine learning. I do visualization, so I want to put it into a visualization system. So I showed you how to do regex for the first step, synthesize regular expressions. But we can also synthesize SQL, and I'll show you for the second half of the talk how to do visualizations. So let's walk through an example of doing the SQL synthesis. So again, I'm at Berkeley, and Berkeley is a public school, which is, it's great in some ways, but if you want to teach there, that means you could easily have hundreds of students. And so doing something like meetings with your students becomes quickly hard to manage. So the way we did it is we just put up a Google form where we asked students, what's your name, what time do you want to meet? And so now we had all our students sign up to meet, except for the question is, which students do we sort of have to harass to get into the office? So with the questions, which ones didn't sign up? And so we want to use synthesis to generate the SQL to do this. So now we actually have two data sources. One is the Google's form I just showed you. Now we have all the list of students who did sign up. And we want to somehow compare that to the list of students in the entire class that we got at the beginning of the semester. So we want to just create the SQL statement that kind of shows kind of the difference between these two. And so we did exactly that, where, OK, we look at on the right, we look at this set of students who signed up. We want to filter those out of whatever result we have. Like, we don't want to see those, because they're already good. What we want to do is we want to take students from the list of all the students and show the ones from there who did not sign up. And so this turns into the notion of like a positive example and a negative example, or a counterexample. So we'll pick Paul Janice in green from the set of all students, because she didn't sign up, so we want that in our result. And we'll pick, who's this, I guess, Smith Berkeley, who did sign up, and so we want to filter him out of the result. So we'll mark him as red, as don't show this guy. We hit the next button, and again, this is real app, I don't have internet connectivity here, so I didn't want to step through it. And then what we get out in about just 70 milliseconds was that exact SQL statement, which gives us the set difference. And what's more, we get the SQL statement, we can verify it there, or we can just look through the actual result of the thing and say that, yes, all these students were ones who did not sign up. And in this case, again, we actually, instead of doing the brute force, we used, that might have actually been with Rosette, where we automatically turn into SAT solver formulas underneath. Cool thing here about this is you might be sort of wondering, well, Vio is showing you all these small programs. What about bigger programs? Like maybe half the time in DSLs, half the times I'm in C or something. And there's some kind of interesting trends here that I think are worth understanding. So what I'm showing here a plot is over the past decade or so. I'm going to kind of compare a few things. So the first one is, everybody in this room should be happy about, is the median programmer salary. On a log plot, like, it looks kind of flat, but it actually did go up, and it looks like we're going to keep going up, so that's kind of good. But we're kind of expensive. And likewise, something we want to compare this to is how much code that we actually need to deal with. So I took one of the bigger projects out there, which is the Linux kernel, and I'm showing in terms of thousands of lines of source code. And we see that over 10 years, yeah, maybe it goes up one magnitude. And so we know, like, program salary goes up a little bit. Now, amount of code we have to deal with goes up a little bit as well, maybe a bit faster. But other things go up a lot faster, and those are where things get interesting. So the first thing is, let's take a look at the speed of the fastest supercomputer. And like every year, we come out with new supercomputers. And that's, every, 2 years, it goes up a magnitude. And so what that means is, essentially, brute force search, eventually, if this keeps up, will actually let you kind of hit that barrier of code size. So that was the first example I showed you of regular expressions. And the second cool thing here is if you look at SAT solvers, which is what we're using if you want to kind of automatically do a lot of these search heuristics. one way to measure stat solver performance is to look at how many thousand variables it can solve. And so I just did 2 data points and drew a line, but in the beginning, about 10 years ago, you could do about 1,000 variables using a stat solver, and now you can do, what is this? 1, 2, 3, 4 magnitudes more variables. And so that's pretty promising. It's kind of matching Moore's law, which is kind of neat. And so what that means is not only do we get the brute force, but we also get smarter algorithms. And put those together, we're able to do bigger and bigger code. So I don't want this talk to be a bait and switch. So I talked about thinking DSLs. So I think we're now kind of on a similar page for what I mean by program synthesis. So now I want to turn over to how we're using this for enabling new types of visualizations. And so kind of a backstory here is one lesson from my PhD was that trying to write a multi-core browser in C++ manually that takes a few years. And so as an offshoot of that work, I started making some language work to automate that process, to write a lot of that parallel code for me. And what I'm going to be showing you here is actually an offshoot of that project where instead of asking you to install the multi-core browser that I was building, I'm going to actually be able to deploy in today's browsers and sort of deploy as a library in parallel JavaScript. So let's go through another demo, just so you know what I'm trying to achieve here. So here we go. OK. So here I'm showing you as actually just running stock Safari, and I'm just showing you actually sequential visualization using normal JavaScript and Canvas. And this is the stuff that you might be able to do today if you wanted to. What I'm showing you here is actually election data. So 100,000 polling stations. Unfortunately, I can't tell you from who. Like, there are just various contractual obligations here. But it is a pretty suspicious election. And what you're seeing here is for each one of these little squares, like this red one over here, that represents one polling station. The more red it is, the more they voted for the incumbent. So here they voted for the incumbent. The more white it is, like, I don't know if we have a nice white square somewhere. I don't know, one of these squares, they voted for some other party. And as you zoom out, you see that most of the country is actually kind of pinkish. And so actually the size of each square represents how many people voted. So actually, here's a white one right here. And it's kind of small, so it's a small district. I mean, small town. And what you can see is that I arranged it into districts, and so you can see this is a bigger district than that district, for example. So one way that people look for fraud in an election, and one of kind of the first things you do is you just look at voter turnout. Like you don't expect to have 100% voter turnout. That means like the president's voting for you or something like that. So I set up this. I don't know if you guys see in the bottom this slider. It's just normal jQuery. So I'm going to filter the data points based on voter turnout. So here we see is all the towns that had a voter turnout of about 20 to 40%. Maybe let's look at towns where the voter turnout was 60 to 80%. So okay, more people turned out at 60 to 80 than at 20 to 40. But you saw that in normal browser, this is kind of a little slow, right? Like, that's not, I don't know. If I was a company, I wouldn't want to be showing my data analysis this way. I don't know, people differ on that. But so here I'm actually using the same visualization. Actually, I have a compiler that spit out the plain JavaScript version, but I spit out a GPU accelerated version just from the same source files. And so let's do that same thing. Let's take a look at, here are the towns that voted in 20 to 40%. And then let's try to ask a question like, what's the biggest voter turnout? Like, where do most people, was the typical turnout for this country? And so most people turned out in 45 to 65%. So if you're actually very curious, you can probably figure out which country I'm talking about just by this statistic. So it's kind of cool. But we're looking for fraud, right? And so the thing you really want to look at is let's take a look at all the places that turned out, I don't know, let's do 80 to 100% turnout. So here are all the towns that probably some suspicious like ballot stuffing is happening because too many people turned out. So what we're going to do is we're going to highlight all of those in black. So take all those suspicious ones. And now what we do is we're going to zoom back out. And this starts to be a little cool. It's like a little cancer spreading through the country, where we know some parts of the country are entirely suspicious. Others are kind of in between, while others look pretty okay. And those are generally this more voting for the not for the incumbent. So I'll do one last step here. I want to point out that right now the ruling party won by a nose hair. It's like 50%. So if we take all those suspicious ones, instead of just throwing them out, let's replace them with exit poll data OK, so now the incumbent's lost. So that means the other parties, if they formed a coalition, they could have overthrown the incumbent. So this is pretty significant stuff. And they probably could have just done it by going through a few districts. OK, so I want to point out a couple things more about the technology going on underneath here. First part is, I'm still showing all 100,000 data points, and you can do the normal GPU type stuff, pan and zoom. But the kind of cool thing is I'm also doing this filtering in real time. And so that means I have to relay it out as well. I'm not just rendering. So this is not the normal WebGL stuff you see. OK, let's jump back here. So in particular, I want to point out 3 things that I think are important about this system and why I've been putting time into being able to code it. The first part is I'm able to show 2 to 3 magnitudes more data without killing the experience. So if you're again, if you're a data company, this is actually pretty significant for what you can show to your customers. The second part is once you have that performance, you actually do new types of visualizations. I was just showing you how to do a tree map, but I've actually already invented one new type. Unfortunately, I don't have time to show you, but it's in creating new possibilities for how we can explore these data sets. So that's pretty cool. Last bit, and this is I think a little more obvious stuff, is OK, instead of writing it all in raw WebGL, we can use high-level languages. It's deployed on the web, which means that we can run on different browsers. We could share it, whatever. But at the more high level, I think those first 2 points are what's fundamentally different, independent of the platform. OK, so the last bit I want to talk about before I jump back into what synthesis has to do with it, and which is, I'm guessing I want to talk about this because otherwise people will probably ask, is what's the actual guts underneath? The idea is it sort of looks like a normal browser. So let me get a little pen here. So normal browser, you get a bunch of HTML and CSS you download from the network, and then all of a sudden you run through a bunch of native C++ components. You're going to parse the files. Once you know what the DOM tree looks like, you're going to want to say run your CSS selectors. For example, take all the pictures and give them really thick borders, something like that. Now that you have pictures with thick borders, you're going to have to relay everything out because you're going to have to say, oh, I need to give it a lot of space because the borders are really thick. And once we know where all the elements go and what size, then we can render it normal scene graph type stuff. So essentially, we're just outputting a bunch of pixels. And now we can put it to the screen. So this is pretty simplified. JavaScript's there somewhere. The cool thing, what we do is instead of relying on the normal browser's native components, because we can do parallelism, we could do better. So the idea is we actually ship a JavaScript library that sort of emulates the normal browser components. And again, instead of shipping a web page, we write some different DSLs that kind of look like normal web DSLs. And we'll run them through a compiler to just make things a little easier. The basic idea is the stack looks similar, but parallel. So we're going to have a parser.js, except for now it's going to use workers to be multi-core. And after that, we're actually going to dump it all into the GPU and actually not only just do parallel implementations of all the components, we're actually going to be running them the entire animation loop on the GPU. And that's a big deal, because if we're dealing 1 million data points in real time, you don't want to be shipping that between the CPU and the GPU in every second or every round through the interactions. And so we'll have our select engine, our layout engine. We're using something called WebCL. I'd love to talk to you after about what that means. And then more for the rendering step, the more traditional use of WebGL for that part. And again, I want to stress that it's important that we're not just doing acceleration for the rendering, but we have to hit the other parts as well, or we'd just be bottlenecked entirely on those. So in terms of getting back in terms of context of the talk, the important parts are twofold. One is to actually be able to write parallel code for all this stuff. We're actually using DSLs. It just makes the problem more manageable. And then for the layout in particular, we wanted to make it really expressive. And here I'm using synthesis to actually let us do that. So let's walk through that, the layout DSL that uses synthesis. So the task is actually, we call it the fast tree language, is our DSL. And the task is similar to what you'd actually have today on a web page, where we have our data, which is a tree. For example, maybe it has a horizontal box somewhere. And the layout language is supposed to figure out what goes where. So in the case of a horizontal box, it has to figure out that the width of the overall box is the sum of the 2 child widths. And the way we do this is actually, it's kind of like CSS, except for we want to do things you can't do in CSS. For example, maybe we don't want boxy layouts. We want a radial, putting stuff around a circle. So we're going to want to add the ability to describe constraints. And this is something kind of formally equivalent to something called an attribute grammar. If you're familiar with CSS and constraints, think of it that way. If you're familiar with attribute grammars, think about it that way. So as an example of writing let's say you wanted to find your own HBox widget, and this is sort of like how you do it in CSS, but a little different. We'll say, OK, let's take the HBox nodes, And then we're going to say that, oh, maybe in the document we expect the x and y attributes to be provided. And then as part of the constraints, we're going to try to solve the width, height, and maybe radius. I don't know why I have a radius here, but like CSS doesn't have that, or like a radial layout, so maybe we can add in things it doesn't have. And the idea is then we're just going to write constraints. So for example, for the width, normally in CSS you just say like 50 pixels or 100%. But here we can actually say width of a box is the sum of the left width and the right width. And so we'll write all those out. And this is pretty much like almost the entire language is a bit more. The key part is that there are a couple of constraints on it, or restrictions on the language. The first part is, even though I give you the ability to write these formulas, they're a little bit restricted. Basically, they have to be local. So if you're talking about the widths, they could only be about the widths of the parent nodes or the child nodes, so kind of that same region of the tree. And the second thing is actually, again, if you know CSS, you're used to this. You can only define a constraint once. You can't define the width to be both 50% and 100% of the parent. We're already used to that today. In this case, I'll actually flag that as at the compile time as an error that your constraints don't make any sense. But otherwise, it's kind of business as usual. So using this DSL, we've actually been able to do a bunch of stuff that normally you'd have to go into JavaScript for, but now you can stay in our DSL. And so then kind of this enriched CSS. I'm going to point out two particular ones. So on the bottom left, you're seeing actually not just a 2D visualization, you're seeing a 3D visualization. And so this one was very useful if you have time series data, like a bunch of stock charts, like hundreds of those, and you want to kind of quickly get a feel for what's going on there. And if you just did normal as a 2D plot, it would just be crazy. The one on the top right is also kind of cool. You might recognize that as Wikipedia. And so we actually specified the CSS language itself, like formally specified CSS, using this DSL I just showed you. And now actually Mozilla is working on a new browser that's using kind of the concepts I showed you here, where we found parallelism in that in the CSS layout language, and they're using that to build a new layout engine. And so that was kind of cool. Okay, so let's get closer to synthesis. So I showed you you can write our layout in our DSL. You want to run it through our tool, and we're going to spit out parallel JavaScript. The question you should be wondering right now is, well, what does that parallel JavaScript look like? Whenever you're talking about synthesis, it's very important what the output language is, because that kind of controls your ability to actually generate good code. So luckily, in the parallel computing community, we've kind of settling on this notion of parallel patterns, that if you're doing high-performance algorithms, you'll talk about different patterns. If you're doing compilers, you're going to say, oh, these are the patterns I support. And this is kind of the rubric. And so here I actually just show you some examples. So for most people here should be familiar with MapReduce. So that's, in a sense, that's a pattern about the data dependencies between your tasks. But there are a whole bunch of other ones. In the case of layout languages, we're interested in tree traversals. And so here I'm going to show you how you actually do a layout engine as a tree traversal. And again, this is the type of thing that we want our synthesizer to reason about. So in this case, we're going to do our little language of horizontal boxes in 3 traversals. So in the first traversal, we're going to solve all of the width and height attributes for every node. And so we'll do a traversal bottom up. As soon as we know the width and height for the children of a node, we can compute the width and height for that node. And so we just do this recursively. And then once we have all the width and heights, we can compute all of the x and y coordinates. And this will be top-down traversal over the tree. So that means once we know the position of one node, we can go off and compute the positions of its children. And we just recur. And you can do this for however many tree traversals you want. And kind of for different types of visualizations, you probably have different ones. And there are 2 important parts here. The first one is that within each traversal, there's a lot of juicy parallelism, because these trees could be really big. So for example, in that first traversal, we're kind of going bottom up. And you can view at the bottom of the tree, we have a bunch of threads. And whenever those threads finish, then we can compute the parent of those threads. It's kind of a logical join. Likewise, maybe it's a little simpler to understand is for the second traversal, where we're kind of going top-down through the tree. Whenever we compute the x and y attribute for one node, we can do a logical fork, and we run different threads for different parts of the tree below. And you can kind of do this all the way down. I'm going to point out that here, I'm just talking about identifying the parallelism in the computation. This isn't necessarily how we run it, but when we give it to the runtime, now it knows kind of the pattern of parallelism there, and it could do a lot of cool optimizations. So I'll get to that. The second cool thing here is, again, we're doing this offline. You can think of this as when you're compiling your browser or when you're compiling your JavaScript library, like part of the minification step, something like that. So we will find a schedule. We want to find a schedule offline such that no matter what data set we push through, let's say we put in different election data, that the same schedule is still safe. That is the correct way to parallelize it. OK, so now just to make this make sure this is very clear, this notion of a schedule is an actual real object in our system. So kind of walk through a little quickly. Let's get that pin back. So here what I'm saying is there are two traversals to do this language of, I guess, horizontal and vertical boxes. So the first traversal is bottom up, so there's this arrow here. And when it visits a vertical box node in our tree, we'll compute first the width attribute and then the height attribute. And same thing for the horizontal box, we'll compute the width attribute and then the height attribute. So it's kind of a schedule. And the idea is, what to actually run there, we just go back to our CSS that we wrote before, that normal constraint stuff. So for the horizontal box, when you hit the width, we just run that with computation. And in this case, we have two traversals. So you do one, semicolon, which sort of waits, and then until that one finishes and do the next. And once we have this pattern, and I think I'm really hammering this home, but I really want you guys thinking, if you think parallel computing, you better be thinking patterns. So I don't feel too guilty about this. So to do a tree traversal on a GPU, there are kind of two things we want. There were two reasons actually we want to do it. The first one is we just want lots of parallelism. So GPUs generally can support more parallelism than other parts of your hardware today. And the second part is, because we want to do other parts on the GPU, you never want to move the data off the GPU, or you want to keep it there in a pipeline as long as possible. So we do want to map the computation down. So in this case, let's say we're doing a bottom-up tree traversal. We're going to do something pretty simple. It has a fancy name of level-synchronous breadth first, but conceptually it's pretty obvious. You take the last level of the tree, we do a parallel for loop over it, compute all over those. Once all of those we compute all those, we have all the information we know to compute the next level. We run another parallel for loop, et cetera. We just go all the way up the tree level by level. So that's easy peasy. Where the hard part really comes in here is that GPUs, the memory is all weird. It's SIMD, it's vector, it's really, these are all synonyms for painful. Don't put that on record. So what we really need to do is you have to do something called flattening. And so let's take our tree again. And remember, each node has a width, height, x, and y attribute. So actually, first of all, we want to take our tree, we want to put it into arrays, because GPUs love arrays. And really the important part here is that on a level of the tree, all the nodes are next to each other, so that when we do the for loop, it's really just burning through an array. And the weird thing is, actually, it has to burn through a bunch of arrays. So if a node has four attributes, like maybe we're solving the width, height, and x and y, we can't actually put those all next to each other as one object. We have to split it into a bunch of arrays. And so this becomes very crazy coding, and this is why all the shader people don't really like data structures and things, and it takes forever. Be nice to your graphic designer. So the cool thing is that because we're using a DSL, we can just do all these transformations automatically. That's compilers are awesome. So getting back to synthesis, now that you know the code I want to generate, and the real challenge we found is actually writing those schedules. And imagine we had some magical automatic parallelizations thing that will come out with that schedule for us. That's actually not enough. So let's say I made that tree map, but then I have a version bump because we're always innovating. So if I do a little change to the constraints, I might introduce some data dependencies. And so how I schedule it might have to change a lot. And actually, it might be really bad how I change it. Maybe it's a bug in how I change the spec because it just kills the parallelism. And so the idea is, instead of just having the schedule be the output of the compiler, we also want the schedule to be the input. So this is kind of weird. And I'm going to walk through an example of what this means. So here I'm showing actually the schedule for the CSS, a multi-core CSS layout engine. I'm actually not showing all of it. Like you see, I have all these underscores where I'll say do a bottom-up traversal, but then I do underscore and I don't really specify the rest. And this is what synthesis gives you. It's it lets us only specify parts of the program that we care about. So in this case, by me not saying what actually gets computed in a traversal, I could say, oh, let me trust the synthesizer to pick those. So if I change the spec and all of a sudden the width and heights can't be computed in the first traversal, like the one over here, maybe now they have to be computed later in this, I guess, fourth traversal. Because I left an underscore there, that meant I gave the synthesizer the freedom to move those computations. However, there are and that's great. So now I don't have to worry about that type of parallel computing. But there are other cases where I don't want the schedule to change. So for example, if we look at these last two traversals, they're parallel, which is great, which is the whole point of this exercise. However, if I change the constraints, I might introduce a data dependency there, where, for example, now they have to be a sequential computation because it just has to be a recursive tree traversal or something like that. the synthesizer will actually reject that change. So say, oh, you changed your layout widget in a way that breaks the parallelism, or the way you intended the parallelism to work. And this is kind of deep. So my kind of claim here is that just as we had to come up with a structured approach to sequential programming, I'm claiming this is sort of a structured approach to parallel programming. And here's some examples of how we used it. If I needed to share a visualization with one of my coworkers or one of my colleagues, I didn't want him to break the parallelization scheme. So this helped me share code with them and let me communicate the parts that were important. Likewise, when I was trying to work with just on my own to figure out how to parallelize something, I was able to test ideas. I could leave holes and let the synthesizer see what it could do. Likewise, if I expected it to do something but it couldn't, it became a debugging tool. This is all just by letting me kind of sketch these schedules. OK, so kind of getting close to finishing up here, I'm going to leave you with a couple of thoughts. So the first part is, I've shown you doing synthesis for a lot of the steps and languages used for data science and data programming, like the regular expressions, the SQL, and like how to build these like high-performance visualizations. But we've actually, our group and others have also been looking at a lot of other domains. So here's some ones that like I can talk to you after about if you're interested in. But I want to point out a few really fun examples. So the first one is synthetic biology. So if you build a biology circuit, the output is something like Tylenol or, I don't know, biofuel. Like, these are things we would like to be able to generate, right? And what the program is actually the protein activation network. And so now the synthesis task is to figure out what is the synthetic biology, the protein network that we want to build such that we can generate biofuel or Tylenol or cheap drugs or something. The next one is on the next row is on user interface layout. So I showed you how to build the kind of low-level kind of schedules for it, but the question is, how do I write the kind of the CSS and the constraints to begin with? And there, again, you'd like to do stuff by example, and so we actually have some cool stuff. And the last one, I think, will appeal to maybe to the strange loop crowd especially, which is type systems, where nowadays, if you're building a type system, you probably want to start with ML. Like, if not, you probably have a good reason not to do that. But because you're designing a new language, there's probably something really cool about it, and you're probably, if you would like to encode some of that knowledge into the type system and check some extra interesting properties. But that could get really hard, and we have like history of just broken type systems in production languages. And so the idea is here, just how I had to put in question marks and underscores for stuff I wasn't sure to put in, it'd be nice as part of your type system, you just put in, well, I need to have some sort of type rule here, and then I'll figure out what the rest is. And I can point you to a pretty fun example here that we're working with recently for some pretty security critical stuff. And so with that, I'm going to finish with the last thought, which is one way to think about synthesis languages is that a lot of times when we're programming, it sort of feels like we're working for the compiler, but that's kind of like backwards. So don't do the compiler's work. Like, use program synthesis. All right, thank you.